Okay, yeah, let us begin with the next session. So the next session will be on sample and hold circuits. So these are, so overall, if you see, we are building towards some, basically we started with op amps and fully differential amplifiers. Now we'll be discussing sample and hold circuits, and in the middle we discussed references. So these are basically building blocks of mixed signal circuits. Eventually you will have some kinds of, if you look at, for example, an A to D converter, it will have some voltage reference, some front end amplifier, and some sample and hold circuit, and then followed by various architectures of the analog to digital conversion. So, or and for example, what we will be discussing in tomorrow's and after tomorrow sessions will be about comparators, and day after tomorrow we'll be looking at high speed links and all. These are all circuits which uh, broadly use some kind of switching circuits and analog circuits together, and we are looking at the basics of those. So today we will be looking at, in this session, we'll be looking at sample and hold circuits. So what is the basic operation of sampling and sample and hold? Basically, sampling operation involves extracting values of an input signal at specific instants of time. Okay, so if you look at it from a signal processing point of view, it's basically conversion from a continuous time signal to a discrete time signal. So conversion from continuous to discrete involves generally two steps. When you do sample, when you multiply, ideally you should be multiplying with delta of t. But when you have a sampling switch, essentially what you do is every time you close the switch, your output reaches to the value of this voltage at of corresponding to the input at that instant of time. And once you open the switch, it will basically stay there. So this is the basic sample and hold operation. An ideal switch which has zero on resistance and infinite off resistance, if you give it an input as a switch signal as an impulse signal, an impulse signal will have area under the curve as 1. It has a non-zero value only at time t equal to 0, and it is 0 everywhere else. So when you multiply these two, you should be getting a discrete time signal. But when you use it as a switch, essentially what you get is a sample and hold signal. And conversion from continuous time to discrete time usually involves two steps. One is first is sample and hold, and then you discretize it. So when you have a discrete time signal, it's not that the value of the signal is 0 at these in the intervals of in the middle. It's just that it is not defined. Okay, for example, you will have in the discrete time signal, you will have timestamps of 0, 1, 2, 3, and so on. Okay, it's just that the signal is not defined for value of, for example, n equal to 1.1. Doesn't make sense. Okay, so this ideal operation with sampling operation with an impulse signal requires an infinite bandwidth and is not practical. Okay, so practical sampling generally involves some finite width of the time for which the switch will be turned on. Okay, it's not possible to have a switch driven with impulse signals in practice. So the small duration of time for which the input is sampled is known as the sampling aperture. Okay, so this name aperture generally comes from photographic, what you say, taking pictures using a camera or something, wherein aperture is defined as the area of the lens, or in antennas it is defined as the area over which the signal is captured. In this case, it's a one-dimensional entity. So the time duration over which the input looks at the switch looks at the input signal, that duration is known as the aperture. So practical sampling basically takes the average of the signal over that small period of time for which the switch is opened. Okay, so even here what I have shown with the sampling aperture as a rectangle signal is not something which is in practice, which can be done in practice. So generally what happens is, by the switch on and turning off will follow some smooth curve like that. And over this duration, what happens is that the input signal gets averaged onto the sampling capacitor. So for example, if you have an equivalent circuit would look something like some R on and C, where R on is the on resistance of the switch and C is the sampling capacitor. So the R on has a profile which which basically is open circuit, but when it is closed, its conductance doesn't. So the conductance doesn't go instantaneously to a high value and come out. It follows some smooth transition from off to on and then on to off again. So because of that, what happens is the practical sampling circuit takes the average of the input signal over that duration of time. So for example, if you look at this value at these locations, it's basically the sampled value will correspond to the average of the signal at the sampling instant. Okay, this is generally not exact average, but some weighted average depending on the kind of switch that you have. Okay, so due to finite on resistance, the practical samplings of the practical sampling switches, sampling bandwidth is finite. Okay, so this is what I have just talked about. So whenever the switch closes, you have some on resistance R on, and this looks now like a low pass filter when the switch is on. So within the short duration of the switch turning on and then turning off, within that duration, the output should charge to the value of the voltage that is being sampled at the input, and therefore this time constant R1 and CS should be very, very small compared to the slope of the signal that you're or the maximum frequency of the signal that you're sampling. So this R1 and CS will determine the maximum frequency of your sampling network. So the constraints on R1 and Roff can be R1 and C can be relaxed to some extent by using track and hold instead of sample and hold. In sample and hold, what we did was every time the sampling switch opens, it measures the input value and then it closes immediately. In track and the input sampling control clock is generally a very narrow pulse. How narrow? It depends on what is the resistance of the switch and the sampling capacity that you have, and what is the aperture that your network can handle. So one of the ways of relaxing this very high on resistance and very low on resistance requirement is by using what is known as a track and hold. In track and hold, what happens is that we have a square wave as a clock signal driving the sampling switch. Whenever the switch is closed for half the clock cycle, the output tracks the input. So if you see here, when the switch is closed, the output basically rises and tracks the input. Okay, and when the switch is open, it will just hold the value there. Again, when the switch is closed in the pink region shown here, the output will track the input and hold once the switch gets opened. So this is a track and hold is something which can be made a little more easily as compared to sample and hold, because of the fact that you get some time to follow the input and track it before you actually sample or hold the value at the sampling instant. So what are the sampling instants? The sampling instants are basically the transitions from on to off. Okay, in sample and hold, the sampling instant was at the middle of the small narrow window over which the switch was closed. In track and hold, it's basically when the switch is closing, that is the instant when you're taking the sample. It is possible to make a sample and hold with using two track and hold circuits in a master slave configuration. So just like how you can do a edge triggered flip flop by using two levels triggered latches, similar way you can have this. This can be thought of some kind of a level triggered thing, right? So essentially, whenever the clock level is low, you're holding it, and whenever the clock level is high, you're just tracking it. Similar, just like how you can do a flip flop from latches, you can make a sample and hold network by using two track and hold circuits. Generally, these things are not required as such. So, but if some place you need, you can definitely use two track and holds to make a sample and hold. So when you're having track and hold based sampling, the sampling bandwidth is bandwidth of the circuit in the track mode, and the sampling aperture depends on how fast the switch turns off to on, which also depends on the rise time of the clock signal. So apart from bandwidth and aperture, there are the other things that affect the performance of sample and holder: noise and jitter in the sampling clock, which introduces some variability in the sampled values. So that is the error that can be introduced in the sampling process. Okay, so that's just a quick background of what is sample and hold and what is stack and hold. We are interested more in circuits, how to make circuits which can do this operation of sampling and hold, and what are the things that we need to take care of when we do that. Okay, so an ideal switch has 0 on resistance, infinite off resistance. A MOSFET can be used as a switch if we swing between cutoff and linear. So when you have a MOSFET in cutoff, its impedance is very high, and when you have it in linear region, its impedance is very low. So if you can have a MOSFET which you can switch, if you switch it between cutoff and linear, you can basically emulate the operation of a switch. So when phi is high, in this case, the sampling clock phi, when I say high, it means logic 1 for an ideal switch or greater than threshold for a, in the case of an NMOS switch. The switch is on, and therefore there is a low resistance path from A to B. In the case of a MOS switch, we can calculate the on resistance by using the drain current equations in the linear region. Okay, we have done this yesterday. We'll just quickly go through it. When you have a MOSFET in the linear region, the IDS is given as mu n C ox W by L, VGS minus VTN into VDS minus VDS squared by 2. Okay, this we have derived this yesterday by from first principles of the MOSFET. So for very small values of VDS, the term VDS squared by 2 can be neglected, in which case this becomes IDS becomes proportional to VDS, and Ron can then be found as dou IDS by dou VDS, basically inverse of dou IDS by dou VDS, which is nothing but 1 upon mu n C ox W by L into VGS minus VTN. So this shows that the on resistance is constant. Okay. However, this is only true as long as our approximation of VDS squared by 2 being negligible is valid. The moment you have large signals or large swings across the drain, then your on resistance can change. Okay, and moreover, this assumes that the input is constant. So if the input itself is changing during the sample, during the tracking or anything, then VGS will be changing, which will result in variable on resistance. We'll look at this in more detail in a couple of minutes. Okay, yeah. So let us consider how the MOSFET behaves as a switch when you are charging and discharging any output. So let us so we have a simple circuit here, which is just a MOS operated as a switch and MOS driving a capacitor. Let us say V naught of 0 is at VDD. So this initially the output is charged to VDD. At time t equal to t naught, the switch closes and Vi is at 0. So what happens to the voltage across the capacitor now? So it will definitely start discharging, but in which region will the transistor be? Okay, so initially what will happen is, so I have my drain at VDD. So in this region, if you look, drain is at VDD, gate is also at VDD, and source is at ground. Okay, so this looks like a MOSFET in saturation. Okay, because the drain and the gate are at the same potential. So what will happen is, the capacitor will start discharging through the switch with the transistor in saturation region. Okay, so when the transistor in saturation, its impedance is very high. Basically, it acts like a current source, and the value of the current source is given by it, determined by the gate to source voltage. Okay, and as long as the transistor is in saturation. So in this case, what happens is that the transistor is in saturation until the voltage drops to a value which is VDD minus VTHN. Let me write it on this side. Okay, in this region, it's this transistor capacitor discharges more or less linearly because it's like the current source, the transistor acting like current source in saturation. It's almost linear. Okay, the discharge is linear. The transistor is actually in saturation. Once it drops to less than VGS minus VT, then what happens is that the transistor goes into this. 1 second. The transistor goes into linear region, and then it's the discharge is more or less like how a simple RC circuit would discharge. So essentially, discharge is exponential, and at time t equal to infinity, it will basically reach to 0 volts, right? So this is how the output discharges if the transistor is an NMOS and the capacitor is discharging from VDD to ground. So if you notice here, the resistance of the MOSFET is high in this region. Since the transistor is in saturation, and in this region, basically, as you go, the resistance drops, reduces with time. Okay, as the drain voltage falls to lower and lower values, the resistance keeps dropping to smaller and smaller values. That is, you can just look at it and conclude that from this resistance equation, and even by looking at the graph, you can see that as you go to lower and lower values of VDS, the resistance keeps dropping. So this is what happens when you are discharging the capacitor using through the NMOS. Okay, what about charging? When if V naught of 0 is 0, initially if the capacitor is 0 volts, input is at VDD, and you turn on the switch at t equal to t naught. What happens to this? So in this case, what happens is the transistor starts, the output starts charging up through the MOSFET. In which region is the transistor here? In which region will the transistor be? So this is again the transistor is in saturation, because what you see here is the drain is at VDD, gate is also at VDD, and the source is at ground. So this will be the drain, this will be the source, and this is the gate. So gate and drain are the same potential, which means that and gate to source is greater than VT, which means that the transistor is in saturation. It acts like a current source, but the value of the current source keeps reducing as the source voltage goes on increasing. Therefore, because of that, you get this exponential increase in the output voltage value. So here the MOS is in saturation. This continues until the output reaches a value of VDD minus VTN. Once it reaches VDD minus VTN, the transistor turns off and the output saturates at VDD minus VTN. Okay, so this is how the NMOS basically charges a capacitor from 0 to VDD. It never reaches VDD. So this you might have come across this many times, saying that okay, the NMOS doesn't pass a 1 well, it passes a 0 well. So that is what we are seeing here also, and just trying to figure out in which regions the transistor operates as the output charges or discharges. So once you reach here, the MOS is off. Okay, so I will not go through the same exercise for PMOS, but what I'll do is I'll quickly draw it. So the similar thing happens, it's just that it's the other way around. So what will happen in the case of a PMOS is the output will charge all the way till VDD, but it will be initially in saturation, and saturation until the output reaches VTP, and beyond that it goes into linear mode, and the output rises exponentially till VDD. Okay, and in the case of a PMOS discharging an output from VDD, basically initially the transistor will be in saturation, and the output will discharge only till VDD minus, only until VTP, and this will be MOS is in saturation, and the curve is exponential even though it acts like a current source, because the value of the current source keeps reducing as the output basically discharges from VDD to VTP. Okay, so basically this PMOS is good for transmitting high voltages or good for passing voltages close to VDD, whereas NMOS is good for passing voltages which is close to ground. Okay, so now if I use this kind of a switch for sampling, what happens? What are the problems that we see when you use this kind of a MOSFET as a sampling switch? So one of the problems is, of course, we have seen that what we have seen in this elaborate discussion is that the resistance of the switch is not constant. It depends on the voltage that is being sampled. There are other problems. One of the other problems is clock feed through. So in any MOSFET, you have a parasitic capacitance from gate to source and gate to drain. What happens is, whenever you are sampling, essentially whenever you are let's say using this in the form of a track and hold, when the clock is high, the output is basically trying to follow the input. The moment the clock goes from 1 to 0, the transistor turns off, and that is when you have the sampling instant. So when your transistor goes from on to off, that is when the clock goes from 1 to 0, VDD to 0, the transistor becomes off, and there is a signal coupled from the gate to the output, right? So this signal will produce an error in the sampled value. Now there are two edges of the clock: the rising edge and the falling edge. The rising edge is not of concern, because even if there is an injection of charge in the rising edge, what happens is, soon after the rising edge, the switch turns on. So there is a low impedance path between V input and the output, because of which any additional charge will get absorbed. Okay, what I'm saying is, so if I have a voltage source and a switch and a driving a capacitor, so when the clock goes from 0 to 1, there is a charge injected onto the capacitor. But what happens is, soon after the switch turns on, the equivalent circuit looks like a very small on resistance followed by the sampling capacitor. So even if there is some additional even if there is some additional voltage here, it will basically get charged to be in through the on resistance. So the clock feed through when the switch is turning on is not important. It's only when the switch is turning off that you have taken the sample and disconnected the switch. At that time, any extra charge that you inject onto the output capacitor will just stay there, and that is the one which causes some error in the sampled value. Okay, now we can calculate this, what is the error in the sampled value, by just estimating what is the parasitic capacitance and the knowing what is the sampling capacitance. So if my sampling capacitance is CS and the overlap capacitance is COV, COV is basically the MOSFET's overlap capacitance. So if I have a NMOS like this, there is a small overlap between the gate and the source, and that produces an overlap capacitance. So this overlap capacitance is given by the capacitance per unit area COX, the length of the overlap, which is this length here, into the width of the transistor. So the wider the transistor you use, the more overlap capacitance that you will have. So this delta V is something which produces an error in the output voltage. But one good thing about one not so troublesome thing about clock feed through is that the error is independent of the input voltage. So this error is constant, or in other words, independent of Vn. So whether I'm sampling a sine wave of 100 millivolts amplitude or some 5 volts DC, doesn't matter what is the input amplitude. The offset is only determined by overlap capacitance and the sampling capacitance. So that is one good thing, because this error appears like an offset, and offset is generally easy to correct, unlike non-linearity errors, which are very tough to correct for. Second, more serious problem, that is what we have seen is clock feed through. There is another serious problem which is known as charge injection. So when the MOSFET turns on, an inversion layer is formed, right? So whenever you invert the channel of the transistor, how is the inversion happening? Basically, you are drawing minority carriers from the substrate and changing the type of semiconductor below the channel from P type to N type. That is what happens when you say inversion, right? So if you have a case where the transistor is in linear, when you're using as a switch, the transistor is always in linear region, and you have an inversion layer. So this inversion layer charges will come from somewhere, right? So they are drawn from the substrate or from the drain and the source to form the inversion layer when the switch is turned on. So this is how the picture looks like when you use a transistor as a switch, which is in the linear region. So there is some charge which forms the inversion layer of the transistor, and that charge we can write as, we have seen this yesterday in our review of the MOSFET. The channel charge can be written as WL COX into VDD minus VI minus VTN. So W into L is the area of the gate of the MOSFET. COX is the oxide capacitance per unit area. So COX into WL will give me the total capacitance C of the gate. And what is the voltage across the capacitor? Voltage across the capacitor is VDD minus VI, right? So when the switch is on, what happens is, once the switch is on, V0 will charge to Vi. So when switch is on, V0 will be equal to Vi, and therefore the source and the drain are at the same potential Vi, and the gate is at a potential VDD. Now the charge on this capacitor is given by VDD minus Vi minus VTN. Why minus VTN? We discussed this yesterday. Because for any potential less than VTN, there is no capacitor formed. It's only for voltage more than VTN that you have an inversion layer and the capacitance formed. And for any voltage beyond that, proportional to the capacitance, you will have a inversion layer charge that is pulled up and formed below the gate of the transistor. Okay, that is fine. Now what happens when the transistor turns off? That is at the sampling instant. The moment you turn off the transistor, this charge has to go somewhere. Where will it go? The moment you turn off the transistor, this charge has to go somewhere. It cannot go to the substrate because that is a reverse bias junction. The only path it has is towards the source or the drain. Okay. how much now, definitely depending on the kind of impedances and voltages on the source and the drain side, the split of how much charge goes to the drain and how much charge goes to the source may change. It's very difficult to it's a very complex phenomenon physically, and it's difficult to model. So if you are very conservative in your design and you're designing for a very what you say, a tight specification, it is better to assume the worst case, that all the charge goes to the output. But generally a thumb rule is that you can assume that about 50% goes to the source and 50% goes to the drain. One of the arguments is that, okay, both of them are at the same potential, it's just the impedance difference that matters. So the source side is generally expected to be a low impedance, and so output side is a capacitance which just can take in the charge that you're and that the channel has to get relieved of. So typical assumption is that 50% of the charge of the channel charge goes out into the source side, 50% goes to the drain side, which means that this charge which we have seen here, the channel charge QCH, WLC ox into VD minus VI minus VTN, half of that charge will get dumped onto this output capacitor at the sampling instant. So this is an extra charge. Okay, so that charge will result in a small error in the sampled value, right? So the error in the sampled value is approximately given as QCH by 2 divided by CS. This is the standard Q is equal to CV formula, and we have seen that half the channel charge gets transferred onto the output sampling capacitor. So the trouble is this error in V0, this error depends on Vi. So it's not constant, it depends on Vi, right? Because QCH itself depends on Vi. So this error depends on Vi, which makes the sampling process nonlinear. And this nonlinear error is generally very difficult to correct for, unlike clock feed through, which is a simple DC offset. Okay, moreover, when we have done this analysis of channel charge and all, we assume that the threshold voltage of the transistor is fixed and constant. But notice that in this case, the source and the substrate are not at the same potential. So because of which, what happens is that there is a substrate bias effect which changes the VT dynamically, which means that there will be an additional nonlinear term into how much charge is going onto the capacitor, because this VTN also will change with the voltage that is present on the input side. So because of this very nonlinear behavior, the sampling process, this charge injection introduces a nonlinear error onto the output sampled value, which is something that we should be which one should be concerned about and see how to compensate for it. Okay, so one somewhat better way, why I'm saying somewhat will be clear in a while, is to use complementary NMOS and PMOS transistors to make a better switch. Okay, which we'll see how it has reduced effects of charge injection and clock feed through. So we have seen that a PMOS passes voltages close to VDD well, NMOS passes voltages close to 0 well. So naturally, one would think of why not use both of them, so that you can both of them in parallel, so that you can pass signals all the way from 0 to VDD. So if you look at the setup here, essentially what you need is you need two complementary clocks. So if this is clock, you also need clock bar for the PMOS side, right? So when you want both of them to be on together, so that they compensate for each other's voltage ranges and essentially give you a full range from 0 to VDD to operate on. So if you look at them independently, the on resistance of the NMOS switch looks something like what is shown in this curve here. Okay, it's very low for voltages close to 0, for the input voltages close to 0. As the input voltages reaches close to VDD, in fact this should be VDD minus VTN, this is a mistake. Yeah, as the input reaches close to VDD minus VTN, the transistor turns off and you get a very high impedance. And similarly for the PMOS, when input is less than VTP, the PMOS doesn't conduct well. But for any values of greater than VTP, the resistance keeps decreasing until until you have a very low resistance at Vi equal to VDD. So when you use both of them in parallel, you will get a on resistance which looks something which is shown in red here, like this, right? Which is basically low parallel combination of both of these resistances. So fine. One problem is that we had with the NMOS and PMOS switches was its resistance was not low over the entire range of 0 to VDD. That problem is addressed to some extent in this, saying that okay, you are having both NMOS and PMOS in parallel, so the overall impedance is low. That to that extent it's okay. But since the clock signals are complementary, what we expect is that the clock feed through will have opposite polarity. Okay, and if they have opposite polarity, we expect them to get cancelled. But you have to be careful here. This is true only if the arrivals of the two clocks are very well matched. Why do I say that? Let's say if one of this clock and clock bar, if one of them arrives earlier than the other. Okay, let us say for the sake of argument, let's say clock arrives before clock bar. Okay, a small error because of mismatch in the I should be looking at the falling transition, right? Okay, I'm exaggerating it here for illustration purposes. So if this is clock and this is clock bar. Okay, what happens is if clock arrives before clock bar, the charge injection by during the transition from on to off from the NMOS transistor will happen at this time. So if I see the total charge injected at the into the output, this will produce an error voltage at the output, which is some small positive value when the clock goes from or rather negative value, right? The clock is going from off on to off, so the voltage will shift downwards, right? But what happens is after this charge has been injected by the clock feed through, during this time the PMOS is still on. So what happens is any charge that is in any clock feed through that happens will go through this PMOS transistor and get absorbed into the low impedance of Vin, right? So because of which what happens is that the charge injection by the NMOS transistor will have negligible effect on the output. Okay, then and now the NMOS switch has turned off. After that, the clock bar comes and switches off the PMOS, and during its switch off, it injects the charge because by its mechanism of clock feed through, it injects some voltage onto the output and produces a small error delta V. Now this delta V will not get compensated. Okay, if clock and clock bar had come exactly at the same time, what would have happened is both the switches would have turned off exactly at the same time. The clock feed through because of clock and clock bar would have come at the same time, and since the switch was off, they would have had to go into the output capacitor only, and each would have produced a voltage of plus delta V and minus delta V respectively, which would cancel each other. But any small mismatch in the timing of clock and clock bar will mean that the one which injects charge first or one which produces an error due to clock feed through first, that small voltage will find a low impedance path to the other switch which is still on and basically not get basically will result in the compensation not happening properly, right? So this requires that the clock signals are very well matched. When I say very well matched, it means that matched in terms of time of arrival. Clock should go from 0 to 1 exactly when clock bar goes from 1 to 0 and vice versa. Okay. There's another thing here, that the error due to clock feed through will be minimized if the width of the NMOS and PMOS are equal. Okay, so what does the clock feed through depend on? Clock feed through depends on the overlap capacitance. Overlap capacitance is proportional to the width and the overlap length. The overlap, L overlap, is more or less constant with for a given process technology, but W is something which the designer chooses. So generally, we would want to choose when we are using NMOS and PMOS in parallel. We would have ideally wanted the on resistance of both of these to be almost equal. But in order to minimize the clock feed through, we have to make sure that the clock feed through because of PMOS and NMOS are same, which mandates that we have the same width. Because of which, what happens is that you will end up using a PMOS which has a higher on resistance as compared to NMOS. So if you look at it carefully in this curve, you see that the on resistance of the PMOS is shown to be higher than that of the NMOS. Okay, this is not error in sketching. It has been deliberately shown like that because that is what you will have to end up doing. So, which means that you will have lower resistance for smaller voltages and a slightly higher resistance for higher voltages close to VDD, simply because you use the width of the NMOS and PMOS as the same in order to make sure that the clock feed through is matched. And because the mobility of PMOS is lower than mobility of NMOS, you will have a higher on resistance, right? So this is one of the concerns we have with the transmission gate type switch. Okay, fine. What about charge injection? So since the transistors are complementary, the channel charge injected is also complementary. For example, the NMOS, when the transistor turns off, the charge that is injected is electrons which escape the channel, whereas in PMOS the channel is made up of holes, so those also will escape the channel. Both of these are complementary. If the transitions are well timed, then any charge injected into the output because of channel turning off will cancel each other at the output. This also requires that both the transistors have the same area, right? So what is the channel charge depend on? Channel charge depends on area of the transistor, W into L, Cox into VGS minus VTN minus Vn, right? So this mandates that both the transistors have the same W and L. Okay, again, this is same, just like how in clock feed through we needed to have the same widths of NMOS and PMOS. The channel charge also requires us to have the same width. Okay, and of course also same length. Generally we will use the same length, so that is not a concern here. Okay, the other thing is the error due to charge injection will be minimized if the geometry is same and VTN is equal to VTP, because one of the NMOS will have the channel charge proportional to VTN with a factor of VTN, and channel in case of P channel, this term here would be VGS minus VTP minus Vn, right? So assuming that VTN is equal to VTP, the channel charge will get cancelled. Okay, so this is the concern with this. So essentially, while it appears on paper that okay, if you use NMOS and PMOS, both will cancel each other, clock feed through will cancel, resistance will be low throughout the entire range from 0 to VDD, and charge injection will get cancelled. It is very difficult to exactly match the arrival of complementary clocks with mismatches during fabrication. Even if you design time, if you make sure that everything is exactly matched, because of variations in fabrication processes, some delays will change, which will produce a mismatch, and that will result in an error. Second thing is, even though the switch resistance is low from 0 to VDD, the variation in switch resistance is quite high. Okay, so if you see this, it is the resistance is not constant. It actually goes maximum value from here to here, right? So this resistance in the switch variation in switch resistance with input voltage in turn produces a nonlinearity, which means that if the charging time of the switch during the on when the switch is on will be different if the voltage is for low voltages and for high voltages as you go from 0 to VDD. All these factors put together limit the usability of transmission gate switches, which you are looking for very sensitive applications. Okay, so we need to see other ways of compensating or correcting for the errors produced by all these phenomena of clock feed through and charge injection. So one of the popular ways of compensating charge injection is by using what is known as a dummy transistor. Okay, so in this case, what we have is we have the NMOS sampling switch with a geometry of W connected to the output capacitor. There is a dummy switch here. Its geometry is half of that of the sampling switch. So instead of W, you have W/2. Why that is so, we'll come to in a minute. And the gate and the drain and the source are shorted, so it doesn't have any implications on the circuit operation as such, except for charge injection and clock feed through and those kinds of things. Okay, so when the transistor is turned on, when the switch is turned on, we don't care about charge injection, right? That's what we had seen earlier, because there is a low impedance path to a well-defined voltage. Even if there is a small error, it will get charged to that voltage of the input. So the charge injected during the turn-off transient is what is of concern to us. Okay, so now let us see that what happens here. So you have the channel charge here, QCH, is W into L into Cox into VGS minus VT N minus VI, right? So what happens is the dummy switch is driven by a clock which is of basically inverted clock of the sampling switch. So when the sampling switch goes from on to off, it basically injects a charge which is half of this value here onto the output. Okay, now that QCH/2 is then used up in forming the channel of the dummy switch. So because what happens is once the sampling switch turns off, the dummy switch turns on. And once the dummy switch turns on, it needs charge in the channel. Basically, the inversion layer charge has to be formed in order to maintain it in linear region. Now, where does that charge come from? It basically has to come from source and drain only. So basically, whatever charge is injected by the sampling switch is absorbed by the dummy switch in order to form its inversion layer, and therefore very little or no charge goes onto the output capacitor. Okay, again, that is about the charge injection. And clock feed through, again, there is error in the output voltage due to clock feed through. We have seen it is given by delta V is C overlap upon C overlap plus C sampling into VDD, right? So what is the C overlap in this case? It is width into L overlap into Cox, right? So that is the charge which is injected from the gate to the output capacitor of the sampling switch. Notice that when the sampling switch turns from on to off, the dummy switch goes from off to on. Basically, this gate will have a rising edge. So the complementary edge on the dummy transistor will in turn inject a charge onto the output of what will be the delta V because of by the sampling switch, by dummy switch. It will be equal to C overlap divided by C overlap plus CS into minus VDD, because the transition is in the opposite direction. Okay, now C overlap for the dummy switch is half of that of the sampling switch, but notice that both source and drain are shorted together. So therefore, I will have charge injection from gate to source as well as gate to drain, and both of these will add together and they will compensate whatever is being injected by the clock of the main transistor. Now the question comes is, what about timing? Is timing very crucial here? As long as, if this is, let's say, clock and this is clock bar, as long as clock bar comes slightly after clock, then the correction will be will happen properly. Okay, why is that so? Because you don't want clock bar to come early, because if clock bar comes early, whatever it injects will find a low impedance path through the on sampling switch. First, what you do is you let the sampling switch go off, let it inject whatever charge it injects into the output, and then after some time, after a small delay, if you turn on the dummy switch, it will absorb or inject the negative charge uh, to compensate for whatever error has been introduced by the sampling switch. And that charge will have no other path but to go into the load capacitor and therefore compensate for whatever error is produced by the turn off transient of the sampling switch. Okay, so this basically reduces the sampling, charge feed through as well as clock injection to a reasonably good extent. And its design requirements are much more relaxed compared to using a transmission gate type NMOS and PMOS combination. Okay, there is another way of compensating charge injection. If you don't, that is what is known as bottom plate sampling. Now, what is bottom plate sampling? It's basically uses two switches again in this fashion. So what you have is, you have a switch phi 1 and phi 2. During sampling, of course, both of them are turned on. For sampling, phi 1 and phi 2 are on for sampling during the sampling period. Now the question is, when you're actually taking, or if I say, in fact, if I have to be accurate, I should say during the tracking period. The sampling is just turning off the switch, right? So now when you want to turn off the switch or take the sample off, or by stopping the tracking, what you do is you first turn off phi 1. So when you turn off phi 1, what happens is it will inject some charge onto the capacitor. So what is the charge it injects onto the capacitor? It will depend on the Q channel, will depend on WL Cox into VGS, which is VDD, minus VTN minus Vi. But in this case, the source and drain, when the switch is on, are at both zero potential, which means that this charge injection is fixed, or it's independent of, in other words, it is independent of Vn, right? So you turn off phi 1 first, it injects a fixed amount of charge onto the output that only results in an offset error, much better than having a nonlinearity error. And after that, you switch off phi 2. Now, if you switch off phi 2, what happens is all the channel charge that is there has only one path to ground. It is through the low impedance of Vn. It cannot go to CS because there is no path to ground. You can charge a capacitor only if the other plate has some path to pull up the negative amount of charge. For example, if I put delta Q here, I will be able to put that only if there is some way to get a minus delta Q on the other plate. But now in this case, what happens is, since the lower plate is open, it is not possible to charge the capacitor because it cannot pull up negative charge from the other side. Therefore, this charge cannot go into the output node. Or another way to look at it is, there is no path from here to ground. Right? So all the channel charge of phi 2 has to go to V in only. Okay, this is what the ideal picture is. In practice, what happens is there is a small parasitic capacitance here from the bottom plate of the capacitor to ground. Because of that, there will be a very small charge injection, but generally the parasitic capacitance is much smaller than the sampling capacitance, because of which this error due to nonlinearity is suppressed to a great extent. Okay, so this is what is known as bottom plate sampling. Okay, essentially it's nothing. It's just that you use two switches, disconnect it from the ground first, then you disconnect the input of from the top plate. So that will basically ensure that the input dependent channel charge injection doesn't happen. Whatever charge injection you get is now only because of phi 1 turning off, and that is a fixed amount. It produces only an offset error in the output. It doesn't produce any non-linearity. Okay, so that is what is known as bottom plate sampling. There are other ways of doing it. If your input is differential, then what happens is most of the charge injection and clock feed through will result in a common mode error, right? So if you have Vi bar and Vi minus and Vi plus, and you use a simple NMOS sampling switch, this will produce a error due to charge injection, due to clock feed through, and so on. This will also produce the same amount of error. But if your CMR, if your common mode rejection is good, then your output V0 will not have any component corresponding to the charge injection and clock feed through. It will only have a component which is proportional to the sampled value. But of course, this assumes that the process of charge injection is basically second order effect. If the charge injection because of by the lower switch and the upper switch is not same because of small variations in V in, that residual error will not be compensated. So it compensates to a good extent, but not completely. Okay. So most practical circuits need the inputs and outputs to be buffered. That is essentially, it means to say that if your source of the signal is not having a low enough impedance to drive the sampling capacitor, then you will need to buffer the input. So one of the ways of circuit is what is shown here. So what you have here is an amplifier A1. What happens is during the, let me look at it in the sampling phase, which is here. And this is the hold phase. Okay, in the sampling phase, what happens is this becomes like a simple two-stage op-amp connected in unity gain feedback. And what happens in this two-stage op-amp is this A2 is connected with having a gain of 1. If this input is having a gain of 1, essentially what this negative feedback will do is it will try to minimize the error between the two terminals of the input on this side. Okay, so which means that this V0 will be driven to Vi by the negative feedback loop, which means that, and since this has a gain of 1, this also naturally has to be driven to Vi. Okay, so in the sampling phase, all these switches are turned on. So this one and this one, and the equivalent circuit looks like what is shown in the middle here. And the sampling capacitor is charged to a voltage of Vi. In the hold phase, what happens is these two transistors turn off, what is shown in the circle in the first figure, and basically the input side is now disconnected from the output side. So you have a sampled capacitor here, which holds the value of the sampled voltage, and it is buffered by amplifier A2 in unity gain configuration to generate the output V0. Okay, so simple way of arranging using amplifiers and switches in order to get a buffered input and a buffered output. So the input source is the charging of the capacitor happens through an amplifier, which basically doesn't or gives you the drive capacity which the source may not have, and the sample value drives the output through an amplifier buffer. Okay, this is just a way of arranging the circuits in order to buffer the input and output. The problem of charge injection and clock feed through will still be there even in this sampling circuit. But using any one of the previous ways of sampling, by using either complementary transistors or dummy transistors or bottom plate sampling and modifying the middle part of this circuit, you can get low error in the entire sampling process, or you can even make a fully differential version of this. Okay, just a simple way of rearranging whatever we have been looking at. Okay, fine. Any questions still here, or I'll just quickly go over again. So basically, for sampling switches, we want low impedance. In the case of NMOS and PMOS, we see that the impedance is not constant with voltage; it changes quite substantially. And moreover, NMOS doesn't pass 1 VDD close to voltages close to VDD well. PMOS doesn't pass voltages close to 1 well. Other problems we have is clock feed through and charge injection. Clock feed through produces an offset error, not that somewhat manageable. Charge injection is non-linear, more problematic. So one of the ways of compensating it is simple-minded idea is just, okay, I'll use both NMOS and PMOS together. While in principle the idea sounds good, it has a lot of practical problems because clock and clock bar have to be well aligned, and in any case it becomes impossible to maintain constant resistance across 0 to VDD, partly because you need to have a higher resistance for PMOS in order to match the geometries which is required to compensate the charge injection and clock feed through accurately. Okay, so these are all the problems with transmission gate type switches, which is why they are not used for applications which require good or very high resolution. Okay, so one other way of compensating it is compensating for clock feed through and charge injection is using dummy transistors. So the dummy transistor basically absorbs the injected charge and provides the negative charge for compensating for clock feed through. So basically charge injection and clock feed through both are compensated, and it doesn't have as stringent requirements on timing of clocks as is the case with transmission gate type sampling switches. Okay, another way of compensating for charge injection is using bottom plate sampling, or we can even use differential if the input is differential. That helps in compensating for charge injection. And one other thing that we have seen in the end is how to configure switches in order to make sure that how to configure sampling switches while buffering the input and buffering the output from the sampling capacitor. Okay, any questions still here? Yes? No questions? Okay, I think this is fairly basic stuff, whatever we have discussed till now. Okay, one of the ways of sampling which shown here is what is known as fully differential sample and hold. So in this case, what we do is basically the ordering of the switches phi 1, phi 2, and phi 3 is maintained in order to minimize the error due to clock, due to charge injection and clock feed through. So what is done first is during sampling, first phi 1 is turned off. So when phi 1 turns off, what happens is initially phi 1 is on, right? So if phi 1 is on, what happens is both terminals are at VCM of the differential amplifier, right? Both are at common mode. So when phi 1 turns off, the charge injection is a fixed quantity. It just produces an offset error because the voltage across the switch is always at VCM. Okay. After that, phi 2 turns off. When phi 2 turns off, again the same thing happens. Because there is no path to ground, all the charge injection due to phi 2 has to go to V in. And after some time, phi 3 turns off, phi 3 turns on, which completes the sampling operation. Now, in this circuit, what happens is once phi 3 turns on, the equivalent circuit becomes like okay, I'm showing the single-ended version with the charge of delta Q. Okay, so that is how the equivalent circuit becomes, and the output is available through the output of the amplifier itself, which can drive low impedances. Now, this capacitor here is shown in, which is shown with one plate quite thick and the other plate quite thin, is because the thick plate is what I want to represent as the bottom plate. Okay, when I say bottom plate, this is different from what I discussed earlier. This is different from the bottom plate sampling. Here, bottom essentially implies it is closer to the silicon in the actual chip. So if I have my silicon substrate here, okay, if the capacitor is formed in some metal layers here, let's say some mx and mx plus 1, m7, m8, or whichever metal layers it may be formed, the plate which is closer to the substrate, or the plate which is at the bottom in the layout, should be connected on the left side of the capacitor here. Now, why is that so crucial? That is because of, if there is any noise in the substrate, which will definitely be there if there are many circuits operating in the vicinity, that noise, in this case, if this is what is that noise basically gets coupled to the output node of the amplifier. Notice that this switch is on during the hold phase. So any noise in the substrate which is injected through the parasitic capacitance from the substrate to the bottom plate will produce an error in the will not produce any error in the sampled value, because it is directly connected to a low impedance node. So this is a low impedance node. Okay, if I do the other way around, if I connect the bottom plate on the right side, okay, then what happens is any charge injected from here will directly go into the sampled value, and this is basically find a path to ground from the output of the amplifier. So this is a bad choice. So notice that this is different from bottom plate sampling. This is in the layout, physically the one with the plate which is closer to the substrate should always be tied to a low impedance node, because that is the node which will pick up noise from the substrate because of any noise and parasitic capacitances. Okay, so these are the various ways of sampling. In the little time that we have, around 15-20 minutes, we'll look at one last technique, which is known as bootstrap sampling. So what is bootstrap sampling? All the sampling circuits that we have discussed till now, they suffer from distortion due to input dependent resistance of the sampling switch, right? The resistance of the NMOS switch we saw changes with the input voltage. Okay, bootstrap sampling is one technique in which you try to maintain a constant resistance of the switch by maintaining constant VGS across the sampling transistor. Okay, now how is that done? So this is a simple schematic here. Suppose I have a battery of voltage VDD and phi and phi bar. So when the switch is off, this phi bar is closed and phi is open. And of course, the switch is off at that time. But when the switch is on, basically this 5R is opened and this is closed. What happens is this is the gate, the source, drain. So VGS is constant at VDD, right? So because VGS is constant at VDD, the on resistance of the switch is independent of the input. What is the exact value of the input voltage at that instant of time? Okay, so if we can somehow set up this kind of a circuit, then we will be able to maintain a constant on resistance and get a switch with very low distortion. Now, how do we realize this? One of the ways you can say is, okay, battery, something which is not very practical, but you can always replace the battery with a capacitor which is charged to that particular value of voltage. So if you have a parasitic, if you have a pre-charged capacitor which is charged to VDD, and you configure it in a circuit like this, so instead of battery, you have a capacitor, you will get the same function. Now, how will you pre-charge this? You can again use a set of switches to pre-charge the capacitor to VDD every time the clock is the switch is turned on, turned off, and every time the switch is turned on, you disconnect it from VDD and connect it in series with the input. So that is what is shown here. So the complete scheme looks like this. When the switch is off, this gate is connected to ground, and by turning on M2 and M5, sorry, M2 and M3, you charge the capacitor to VDD. Okay, and when you want to basically turn on the sampling switch, you open the switch M6, open these two switches M3 and M2, and close M5, M4, and M4, M5 and M4 to basically connect the gate of the transistor in series with the capacitor to the input. So during sampling, when the switch is off, the capacitor is pre-charged to VDD, and when the switch is on, the input gets connected through M5, M4, and the capacitor to generate a voltage here, which is Vin plus VDD. Fine. So this scheme will basically give you a constant VGS and a gate voltage of Vn plus VDD for the sampling transistor. Okay, now let us look at how to implement this. So what kind of transistors will we use for the various switches here? Okay, let's finish with the easy ones first. Maybe I'll just draw it again. What will M6 be? M6 basically connects the gate of the NMOS transistor to ground when the switch is off. So if I have to connect something to ground, I will definitely use a NMOS transistor to connect the gate to ground. And when should it be connected to ground? It should be connected to ground when the switch is off. So this should be clock bar, right? When the switch is off, that is when clock is low, clock bar is 1, and at that time, this transistor turns on to connect the gate to ground. Okay, now I have a capacitor here. Again, I have M3. What kind of transistor should M3 be? Again, M3 connects the bottom plate of this capacitor to ground. So since it is supposed to discharge a node to ground, we will again use a NMOS. And when does that happen? That happens when the switch is off. So therefore, this also will be clock bar. Okay, this is Vn. Okay, what about M4? What kind of transistor will it be, NMOS or PMOS? M4 basically passes voltage of Vin plus VDD from the top plate of the capacitor to the gate of the switch, right? So it's a high voltage. So in order to pass a high voltage, you need to basically use some kind of a PMOS transistor, right? So what will the voltage of this PMOS transistor be? Gate voltage? We'll find that out in a minute. basically it should be when the sampling is happening, it should be connected to what you say, this switch should be on, and when during hold phase it should be off, right? So this will be also be clock bar. Okay, now what about M5? M5 is same as the sampling switch M1. Therefore, if you are going to, maintain a constant VGS for M1 in order to pass input properly to the output, this same Vin also has to go through M5, M3, and M4 to get a value of Vin plus VDD onto the gate of the sampling switch. Okay, that will happen only if M5 can pass the value of Vin properly from this node to this node. Okay, so therefore the resistance of this M5 also should be constant with respect to voltage of the input. Therefore, what we will do is, and M5 is on whenever M1 is on, so we can basically connect, we can connect gate of this also to the gate of the M1. So whenever you get Vin plus VDD here, both M1 and M5 will have a fixed resistance to charge the output. Okay, so we have finished most of the transistors. All that remains is M2. Again, M2 has to pass VDD, so definitely it should be a PMOS transistor. Now, what should be the gate voltage here? So notice that when the switch is on, so basically this should have been clock ideally, because when clock is 0, the sampling switch is off. At that time, this PMOS transistor should have been charged to VDD. And when clock is 1, the sampling switch is on, and at that time this PMOS is disconnected. But when the clock is 1, the node voltage here is at Vin plus VDD. And if Vin is greater than VTP, it may actually turn on the PMOS transistor. So in order to prevent this from discharging Vin plus VDD to through this low impedance path to VDD, we also must connect this to the bootstrap switch. So basically this will also be Vn plus VDD, and this will also be Vn plus VDD, which will make sure that this transistor is off. Okay, so by using this arrangement, essentially what we get is, we make sure that your gate to source voltage of the sampling switch is always constant at VDD, and because of which you will get very low distortion in the sampling process. Okay, this is what exactly the same circuit I've drawn here. So M2 and M5 both get the high voltage of Vn plus VDD, and all the other transistors basically are driven by clock bar or phi bar. Okay, because of the fact that the overdrive of the transistor is constant, the distortion is very small. Okay, generally if you are looking for some very high, very precise sampling process for, let's say, for high resolution A to D converter, practically any A to D converter which you look for more than 8 to 10 bits will require very low distortion sampling, wherein you will have to use some kind of bootstrap sampling. Okay, any questions about bootstrap sampling as such? So essentially, what is the principle we are doing? If I go over it quickly, the principle is that the problem is that because of the fact that the resistance of the transistor switch changes with Vin, that produces a distortion in the output. So what we do in bootstrap sampling is we try to maintain a constant gate to source voltage between the switch, so that the resistance of the switch is constant. Once you have a resistance constant, any error that you get will be a simple DC offset. It won't be a non-linearity. Okay, it's a linear error, so that can be easily corrected. So the way to do that is, if somehow you can establish a constant voltage difference between gate and source of 1 VDD, then you can make sure that the switch resistance is constant. Okay, so one of the ways of doing that is connecting a battery, but of course in batteries, in practice it's difficult to get to put a battery like that. So we have to use some kind of pre-charged capacitor, which will do the same function as that of a battery. And to keep charging the capacitor to VDD before connecting it to the input, we have an arrangement of switches. And by inspecting each switch where it connects to and which voltage it drives, whether it drives something to ground or something to VDD, we choose NMOS or PMOS transistors and connect them to clock or clock bar. Incidentally, in this case, all the 3 transistors we need only clock bar, and 2 of the transistors we use the generated bootstrap voltage itself for pre-charging the capacitor as well. Okay, so that leads us to this circuit of the bootstrap sample and hold switch. Any questions about this? Okay, so till now we have seen how to reduce the error produced in the sampling process due to charge injection, due to clock feed through, and so on, and how to correct for that. After you have sampled it and you're holding the value, there will be an error in the voltage, output voltage, if your hold time is very high. Generally, if you are having some kind of analog memory wherein you are holding the capacitor value for some time before you read it, then there is always some leakage current which will discharge the capacitor and produce an error in the output voltage. Okay, one of the most common most serious paths of discharge is through the parasitic diode of the NMOS. So in this case, what you have is you have an off switch, and this is where your capacitor is connected, right? So this N plus P diode, which is reverse biased, will have a leakage current, and that leakage current will basically discharge the sample value. So if you want to design a circuit which can hold the sampled value for long times without, or basically reduce the leakage, we can do that by using what is known as triple well transistors. So if you can somehow, or in this case, even if you are using a single well transistor, if you use a PMOS switch, okay, and in the PMOS switch, if you connect the well to the output voltage, okay, so what it means is what I'm trying to say is this. If you can somehow set up a negative feedback circuit or a feedback circuit to read the value of, to read the sampled value and drive the substrate of the transistor to the same voltage. So what this op amp will do is, this op amp is nothing but a voltage follower, right? So if this is V0, this will also be V0. Okay, if you are using a triple well transistor, or if you use a PMOS switch and connect the well to the output voltage, then what happens is you have this diode, in which case both the terminals are at the same voltage, therefore the leakage current will be 0. Okay, so if you set up the circuit like this, you can get very low leakage current and hold the output value for a long period of time. Okay, simple circuit, nothing very different, very new in terms of concept. But just the thing is that you need to have triple well transistors, and also you should make sure that during the sampling phase, this connection of V0 or the bulk drive should not change the VT of your transistor, okay, too much. If it changes too much, then you might have to have some arrangement so that you connect this only after the sampling is done, and before the sampling is done, you somehow disconnect this. Okay, you can set up such circuits to reduce the leakage. Okay, I think with that I will stop here. If there are any questions, we can take them here. These are standard circuits. You can find most of these in these textbooks of mixing analog design. The bootstrap switch, there is a very nice summary given in one of these, in this magazine article by Behzad Razavi. And if you are interested in low leakage switches, you can look at this paper for some very interesting circuit architectures which are very easy to understand. Based on our discussion today, we should be able to follow what are the techniques they use to get leakage currents as low as 10 attoamperes. Okay, so I will stop here. If there are any questions, we can discuss. Otherwise, we will take a break and come back for the lab session. Okay. So was this session useful, or was it that most of the things you already knew in terms of sample and hold circuits? Yes.